The research presented focuses on addressing the binding problem in human cognition, where the brain represents and connects objects within a fixed network of neural connections. The authors introduce rotating features, a generalization of complex valued features to higher dimensions, allowing for the representation of a greater number of objects simultaneously. This innovation requires the development of a new rotation mechanism. Additionally, a new evaluation procedure is proposed for extracting discrete object masks from continuous object representations of inputs with more than one channel. The applicability of this approach to features created by a pre-trained vision transformer is also demonstrated, enabling the extraction of object-centric representations from real-world images. This work advances a new paradigm for addressing the binding problem in machine learning and has the potential to inspire further innovation in the field. The authors draw inspiration from neuroscience theories, particularly the temporal correlation hypothesis, which posits that the oscillating firing patterns of neurons give rise to the binding of features. The proposed model introduces the concept of rotating features, which are designed to enhance object-centric representations in neural networks. This approach builds upon previous work in machine learning, drawing inspiration from neuroscientific theories. The key innovation lies in the creation of a feature matrix, Z-rotating, that includes both magnitude and multidimensional orientation components. This matrix is processed through a neural network layer, resulting in the output psi. A binding mechanism is then applied to this output, encouraging features with similar orientations to be processed together while weakening connections between those with dissimilar orientations. This leads to the emergence of object-centric representations, as demonstrated by the model's ability to differentiate between objects in real-world images. The binding mechanism is crucial for this process, as it incentivizes features representing the same object to align and features representing different objects to take on distinct orientations. This effect is illustrated in Figure 3, where the binding mechanism results in features with similar orientations being processed together, while connections between features with dissimilar orientations are suppressed. Without the binding mechanism, the model fails to learn object-centric representations. The model's performance is evaluated on various datasets, including FoodSeg, Pascal, and others. The results show that the proposed approach significantly improves object-centric representations, leading to better performance in segmentation tasks. This demonstrates the effectiveness of the rotating features and binding mechanism in enhancing object-centric representations in neural networks. In the context of object-centric representation learning, this research introduces a novel method called rotating features to enhance the separation of objects in distributed representations. This approach is based on the concept of complex AutoEncoders, which use complex numbers to represent object features in a distributed manner. The proposed improvements include applying a batch normalization mechanism to ensure that the magnitude of the output features is positive and normalized, and utilizing a neural network model that adheres to the layer structure of rotating features. The training process involves applying the model to input images and computing a reconstruction loss function using the mean squared error, MSE, between the original and reconstructed images. The object separation performance is evaluated using metrics such as adjusted rand index, ARI, and mean best overlap, MBO, which measure clustering similarity and intersection over union, IOU, values of the predicted mask pairs, respectively. Experiments are conducted on various datasets, including the 4 shapes dataset, where rotating features outperform standard autoencoders and complex autoencoders in terms of reconstruction and object discovery performance. The results demonstrate that larger rotation dimensions lead to better reconstruction and object discovery performance, with n is greater than or equal to 6 resulting in a perfect separation of all shapes. The proposed method has several advantageous properties, including the ability to scale from simple toy to real-world data, and can be applied to vision datasets by incorporating additional dimensions and applying a neural network model that adheres to the layer structure of rotating features. This approach is implemented in PyTorch and evaluated on a single NVIDIA GTX 1080 Ti. The research paper discusses the capabilities of rotating features in object discovery, particularly in scenarios where objects are diverse in shape, size, and color. It starts by evaluating rotating features on the 4 shapes and 10 shapes datasets, demonstrating their ability to separate multiple objects with varying orientations and sizes. The performance improves as the rotation dimension increases, showing that rotating features can differentiate 10 objects simultaneously. The paper also explores their applicability to multi-channel images by creating an RGB-D version of the 4Shapes dataset. It reveals that while rotating features struggle with RGB images due to color-based grouping, adding depth information resolves this issue. The study further applies rotating features to real-world images using a pre-trained vision transformer, achieving good object discovery performance on the Pascal VOC and FoodSeg 103 datasets. The results highlight the effectiveness of rotating features in segmenting objects across various datasets, outperforming some baseline models and demonstrating their scalability from simple toy datasets to real-world data. In the context of object-centric representation learning, the proposed rotating features model introduces a novel approach to address the binding problem in machine learning. This model leverages pre-trained features and introduces a new evaluation procedure that scales from toy to real-world data. The key improvements include learning to distinguish the correct number of objects automatically, generalizing well to different numbers of objects than observed during training, expressing and processing uncertainty in object separations, and being very efficient to train. The rotating features model's continuous object-centric representations are evaluated using various clustering methods and hyperparameters, such as k-means and agglomerative clustering. When the number of objects in the test images is unknown, evaluating rotating features with agglomerative clustering preserves a fairly consistent performance across varying numbers of objects per scene, significantly outperforming other approaches that require the number of objects to be set in advance. Uncertainty maps can be generated by plotting the L2 distance of each normalized output feature to the closest k-means center, revealing higher uncertainty in areas of object overlap, object boundaries, and incorrect predictions. Training the model is also very efficient, requiring less than 3.5 hours on a single NVIDIA GTX 1080 Ti, compared to the dinosaur models which were trained across 8 NVIDIA V100 GPUs. Rotating features create the capacity to represent more objects at once, but currently, this capacity can only be fully leveraged in the output space. Within the bottleneck of the autoencoder, the separation of objects is not pronounced enough, and only up to 2 objects can be extracted at a time. Further research into novel inference methods using rotating features is necessary to overcome this limitation. Despite producing slightly inferior object discovery results compared to the state-of-the-art dinosaur autoregressive transformer model, rotating features still surpass standard MLP decoders. The proposed model explores a new paradigm for object-centric representation learning, sparking further innovation and inspiring researchers to develop novel methods that better reflect the complexity and richness of human cognition. The paper discusses the development of a novel, object-centric model that utilizes the transformer architecture to perform unsupervised scene decomposition and representation learning from real-world videos. This approach, named Genesis, is based on the concept of binding, which allows it to effectively capture and represent multiple objects within a scene in a unified manner. Genesis operates by iteratively refining its predictions through an expectation maximization algorithm, resulting in the extraction of meaningful object-centric representations from raw video data. These representations can then be used for various tasks such as object detection, segmentation, and tracking, without requiring any explicit supervision or labeled data. The authors also introduce a new benchmark dataset for evaluating object-centric models, called Objectron, which consists of videos featuring various objects with diverse shapes, sizes, and appearances. This dataset is designed to challenge current models and encourage the development of more robust and generalizable object-centric learning algorithms. In addition to the introduction of Genesis and the Objectron dataset, the paper provides a comprehensive review of related work in the field of object-centric learning. It discusses several key concepts, including the importance of binding, the role of attention mechanisms, and the use of transformers for visual processing tasks. The paper concludes by highlighting the potential applications of object-centric models like Genesis in areas such as robotics, autonomous driving, and augmented reality. It also emphasizes the need for further research into the development of more efficient and scalable object-centric learning algorithms that can handle complex scenes and multiple objects effectively. The research paper explores the concept of object-centric learning, which aims to understand and segment objects within complex scenes in an unsupervised manner. This approach is based on the idea that objects are fundamental components of perception, as proposed by cognitive scientists such as Elizabeth S. Spelke, 72. The paper discusses various methods for object-centric learning, including those that utilize complex valued autoencoders, 73, transformers, 71, and neural networks, 46, 63, 67, 69, 70, 74, 75, 77. These models are trained using techniques like contrastive training, 73, query optimization, 37, and conditional set generation, 44. The authors also delve into the importance of synchrony in object-centric learning, drawing from theories in neuroscience, 65, 66, 67. They highlight how synchronization can be used to differentiate between objects and their backgrounds, leveraging principles from Gestalt psychology, 42, 43. Moreover, the paper emphasizes the significance of real-world datasets for object-centric learning, referencing datasets like those provided by Cabra et al., 39. It also discusses the role of libraries like PyTorch, 54, and scikit-learn, 65, in facilitating the development of these models. The paper further explores the concept of spatial attention and decomposition, as seen in models such as Space, 45, which utilizes spatial attention to segment objects and scenes. It also touches upon the idea of bridging the gap to real-world object-centric learning, 64, which is crucial for practical applications of these models. In conclusion, the paper provides a comprehensive overview of object-centric learning, emphasizing its importance in understanding and segmenting objects in complex scenes. It discusses various methodologies, including complex valued autoencoders, transformers, and neural networks, and highlights the significance of synchrony, real-world datasets, and spatial attention in this field. This research explores advancements in continuous and distributed object-centric representations, scaling them from simple toy to real-world data. The proposed techniques expand the methodological landscape for object discovery, which may benefit various areas of machine learning, such as computer vision, robotics, and natural language processing. The authors draw inspiration from biological insights, exploring approaches to resolve the binding problem in machine learning, which may advance our understanding of object representations in the brain. The research promotes more structured representations, improving interpretability in machine learning models. The proposed approaches can be applied to complex, multidimensional data, such as RGB images, making continuous object-centric representations applicable in real-world scenarios. The authors acknowledge the potential broader impact of their research, including advancing machine learning, gaining biological insights, improving interpretability and scalability. They recognize the potential for unforeseen consequences and encourage further innovation and interdisciplinary collaboration. To ensure reproducibility, the authors provide a comprehensive overview of the employed model architectures, hyperparameters, evaluation procedures, datasets, and baselines. They published the code used to produce the main experimental results and conducted experiments using 45 different seeds to achieve stable and reproducible results. The implementation details of the rotating features model are provided, including the architecture and hyperparameters used to train the model. The auto-encoding architecture is described in detail, and the activation function employs batch normalization in convolutional layers and layer normalization in fully connected layers. The number of learnable parameters increases minimally for larger values of rotation dimensions, reflecting a mere 2.7% increase. Overall, this research contributes to the development of object-centric representations, promoting a deeper understanding of object discovery and its applications in machine learning. The auto-encoding architecture for rotating features is presented in Table 2, featuring an input dimension of h, w, and c, and a feature dimension of d. The architecture consists of an encoder, a linear layer, and a decoder. The encoder comprises multiple convolutional layers, followed by a reshape layer and a linear layer. The decoder consists of a linear layer, a reshape layer, and multiple transposed convolutional layers. The hyperparameters for models trained directly on raw input images and those trained on DINO features are detailed in tables 3 and 4, respectively. For models trained directly on raw input images, the hyperparameters include training steps, batch size, learning rate warm-up steps, peak learning rate, gradient norm clipping, feature dimension, rotating dimension, image or crop size, cropping strategy, and augmentations. For models trained on DINO features, the hyperparameters include training steps, batch size, learning rate warm-up steps, peak learning rate, gradient norm clipping, feature dimension, rotating dimension, image or crop size, cropping strategy, augmentations, and K. A pre-trained vision transformer model, specifically the DINO model, is employed to pre-process input images and generate higher-level input features. The DINO model features a token dimensionality of 768, 12 heads, a patch size of 16, and consists of 12 transformer blocks. The final transformer block's output is used as input for the rotating features model, excluding the last layer norm and the CLS token entry. To evaluate the learned object separation of rotating features, the output orientations are clustered. The output features are normalized onto the unit hypersphere, and a weighted average is applied to mask features with small magnitudes. A clustering method, either k-means or agglomerative clustering, is then applied to the weighted average. The predicted object masks are resized to match the size of the ground truth labels and smoothed using a modal filter. The final object discovery metrics are calculated by treating in labeled pixels and pixels from overlapping instances as background. The 4 shapes dataset is introduced, comprising grayscale images of dimensions 32 by 32, each containing 4 distinct white shapes on a black background. The dataset consists of 50,000 images in the train set and 10,000 images for the validation and test sets, respectively. The RGB-D variants of the 4 shapes dataset are also described, where the color of each shape is randomly sampled. Here is a combined summary of pages 19 and 20 of the research paper. The authors describe 3 datasets used for object-centric representation learning: 10 shapes, Pascal VOC, and FoodSeg 103. The 10 shapes dataset consists of RGB-D images with 48 × 48 pixels, featuring 10 unique shapes with varying orientations and sizes on a black background. Each object is assigned a unique depth value within the range 0, 1, and a distinct color. The Pascal VOC dataset is a widely used benchmark for object detection and semantic segmentation, and the authors follow the approach of Seitzer et al. 64, for training and evaluation. The FoodSeg 103 dataset is used for food image segmentation, and the authors apply the same pre-processing steps as for Pascal VOC with additional random augmentation. The authors also describe several baselines for comparison, including Complex AutoEncoder, CAE, AutoEncoder, block masks, slot attention, slate, DINO k-means, dinosaur transformer, and dinosaur MLP. The block masks baseline involves dividing the image into a specific number of columns and distributing blocks evenly across the columns. The authors present a theoretical investigation into the capacity of rotating features to represent many objects simultaneously. They plot the minimum cosine similarity achievable between any pair of points when placing a specific number of points onto an n-dimensional hypersphere. The results show that starting from 10 points and with n large enough, the minimal cosine similarity barely increases, indicating that rotating features should be able to scale to larger numbers of objects effectively. Additionally, the authors describe the implementation of slot attention, which involves a hidden dimension of 64 across the model and modulation of the decoding structure as outlined in Table 5. The architecture used for the spatial broadcast decoder in the slot attention model is also provided. We investigate the behavior of minimal cosine similarity between points on a hypersphere by implementing an optimization procedure. This is necessary due to the lack of an exact solution for optimally distributing a variable number of points on higher dimensional hyperspheres. We observe that regardless of n, we can always separate 2 points by a minimum cosine similarity of 1. With rotating features, we introduce a method to learn features with n is greater than or equal to 2. enabling us to add more points to the hypersphere while maintaining small minimal cosine similarities. In our main experiments, we demonstrate that rotating features create the capacity to represent more objects simultaneously. We explore object separation within the bottleneck of an autoencoder utilizing rotating features, highlighting their increased capacity in the latent space. We create a weakly supervised semantic segmentation setup, where we introduce a supervised task in which a binary classifier is trained to identify the classes of all objects present in an image. We train a network with rotating features on a classification task, applying a linear layer to map the latent dimension of the encoder to the number of possible object classes. We use the resulting loss value alongside the reconstruction loss to train the network. After training, we leverage the object separation within the bottleneck of the autoencoder to assign each individual pixel a label representing its underlying object class. Our results indicate that on the MNIST-1 shaped dataset, our approach with rotating features achieves strong weakly supervised semantic segmentation performance, almost doubling the performance of the baseline. However, on the MNIST-2 shaped dataset, the performance falls short, despite achieving strong object discovery and object classification results. This highlights that while rotating features create the capacity to represent more objects simultaneously, the object separation within the bottleneck of the autoencoder is not pronounced enough to separate more than two objects. The research discusses the performance of a novel approach, rotating features, in weakly supervised semantic segmentation tasks. On the MNIST-1 shape and MNIST-2 shape datasets, the approach outperforms a baseline that randomly assigns labels, demonstrating strong performance in creating accurate object masks with correct labels. However, as the number of objects increases, the performance of rotating features deteriorates, particularly when the rotation dimension is set to 2. In contrast, when set to 10, the performance remains strong. This suggests that the choice of rotation dimension becomes increasingly important with more complex scenes. The model also shows promising results on the multied sprites and CLEVR datasets, surpassing the CAE model but still lagging behind the state-of-the-art. The qualitative examples highlight the issue of objects of the same color being grouped together, which can be addressed by using higher-level input features. Overall, the research emphasizes the importance of the rotation dimension in object discovery and the need for further improvements to achieve state-of-the-art performance. The research paper discusses the performance of the rotating features (RF) model on various datasets, including 4 shapes, multied sprites, and CLEVR. On the 4 shapes dataset, RF shows a substantially better object separation compared to the CAE, but it fails to separate objects of the same color. This is evident from figures 15 and 16. The paper also provides hyperparameters for the RF models trained on multied sprites and CLEVR datasets in Table 7. The performance of RF and CAE on these datasets is detailed in Table 8, showing that RF achieves strong results in terms of ARIBG and MBOI. Additionally, the paper includes supplementary results for other datasets, such as Pascal VOC and FoodSeg 103. Highlighting the versatility and effectiveness of the RF model. The research discusses the performance of rotating features in various datasets, focusing on reconstruction and object discovery. Table 9 shows a significant improvement in both MSE and object discovery metrics as the number of rotation dimensions increases. This outperforms standard autoencoders and complex autoencoders. Tables 10 and 11 detail the impact of color complexity on the RGB and RGBD datasets, highlighting the importance of depth information for better performance. Figure 17 qualitatively compares the performance of rotating features with different numbers of rotation dimensions, demonstrating sharper reconstructions and better object separations with a sufficient number of dimensions. The findings emphasize the capacity of rotating features to separate multiple objects and their adaptability to varying dataset complexities. Rotating features, a novel approach for object separation, is demonstrated on various datasets, showcasing its capabilities and limitations. Figures 18 and 19 illustrate the application of rotating features to the 4 shapes RGB, D, and 10 shapes datasets, respectively. The addition of depth information in the RGBD dataset significantly improves object separation, although the model tends to group one object with the background. In contrast, the 10 shapes dataset demonstrates the model's capacity to separate all 10 objects with a sufficient rotation dimension n. Figures 20 and 21 demonstrate the applicability of rotating features to real-world images by leveraging higher-level input features created by a pre-trained vision transformer. The model successfully learns to separate objects in the Pascal VOC and FoodSeg 103 datasets, respectively. The efficacy of rotating features is further explored in Figure 22, which compares the performance of various clustering methods, including k-means and agglomerative clustering, on the FoodSeg 103 dataset. The results show that rotating features can automatically learn to separate the appropriate number of objects, allowing for efficient testing of different clustering methods and hyperparameters. The clustering results, presented as mean plus or minus SEM across 4 seeds, reveal that k-means clustering achieves better results than agglomerative clustering. However, agglomerative clustering eliminates the need to set the number of objects to be separated, highlighting its potential as a more flexible approach. The distance threshold, ranging from 0.2 to 1.0, is also explored, with optimal results obtained at a threshold of approximately 0.35. Overall, rotating features demonstrate promising capabilities for object separation in various datasets, with potential applications in real-world image segmentation tasks.